In the last section of Chapter 8, we're looking at a concept that seems to be a little bit unrelated to what we've been talking about, but it actually is. We want to look at enthalpy, which is just a measure of the amount of heat being either given off or absorbed by a chemical reaction. So we've already talked about the fact that chemical reactions can give off heat or thermal energy, in which case they are exothermic, or they can absorb heat from their surroundings, which makes them endothermic. So remember the terms exothermic and endothermic. We're going to refer back to those. We talked about them in general terms previously, but we can put a quantifiable amount on those reactions. So the amount of thermal energy or heat that's being emitted or absorbed by a chemical reaction, as long as you're under conditions of constant pressure, we can quantify that with a function called the enthalpy. So what we're doing is putting a numerical value on the degree of exothermicity or endothermicity. We define this as the enthalpy of reaction. So this is abbreviated as delta H subscript RXN for reaction. This is the amount of thermal energy or heat that is flowing either in or out of the reaction when a reaction occurs at constant pressure. We're going to use the sign of the reaction, either positive or negative, to determine the direction in which heat is flowing. Okay, thermal energy. So if energy is flowing into the system, if it is absorbing energy and it's positive, then that is going to be endothermic. And if energy is flowing out of the system, it is emitting heat, it will have a negative sign, and that will be exothermic. So energy flowing out of a system is a withdrawal, carries a negative sign, flowing in, positive sign. So just to emphasize again, exothermic and endothermic. So it becomes very important with enthalpy calculations to pay attention to positives and negatives. What is the sign for the final answer? Okay, so just to graphically represent that again, in graphic A here, we show an exothermic reaction in which we are starting with our reactants at some higher energy level. Energy is being released, okay? So heat of reaction is negative, energy level drops, and then the products are at a lower energy level than the original reactants. The endothermic situation is just the opposite. Our reactants are starting at some level of energy. They are absorbing, so they're moving up. And then our products stop at some higher energy level. They have absorbed more energy than the original reactants have. So looking at the sign for the change in enthalpy of a reaction, we've already said when we have energy flowing out of the reaction, it is negative. And an example of this would be the combustion, any combustion, but we're looking here at the combustion of methane. So methane is the main component of natural gas. So if we combine that methane with oxygen in the air, remember a combustion, we get carbon dioxide and water. Those are our two products. Now we can actually measure that change in enthalpy. So when you see these values right here, this delta H reaction is equal to a negative 802.3 kilojoules. These are what we call empirically determined values. That means they were experimentally determined. Somebody in a laboratory setting gathered this data, and it's been gathered over and over and over again. Random errors have been averaged out of it, and we've arrived at this experimental value. Okay, so this is empirical data. So here's the value that we have for methane. Because it is negative, that tells us that this is an exothermic reaction. Okay, it's exothermic, negative enthalpy of reaction. We know that a combustion is exothermic. We know when we burn something, it gets hot. It gives off heat to its surroundings. And if we're part of the surroundings, we feel that heat. Now, what's different, we've talked about, endothermic, exothermic, energy in, energy out. What we're doing is putting a value on it. So in that last graph where we had energy and we had the products, or in this case, let's see, we're going to start up here, products, and they drop down to the reactant level. What we want to do now is put a number on that drop. We want to know how far did it drop. We want to quantify it. And that's what the 802.3 tells us, the magnitude of heat that gets emitted when this reaction occurs. 1 mole of methane reacts with 2 moles of oxygen. Now, if we look at the reverse of that, thermal energy is flowing into a reaction. So this is where we're starting with our reactants at some level, and energy goes up, and we stop at products up here. Okay, so remember energy going here. So energy is flowing in, and we have a positive enthalpy of reaction. An example of this one is when nitrogen and oxygen gases combine to form nitrogen monoxide. When we look at our data here, delta H reaction, we see that it's a positive 182.6. Now this reaction is endothermic, so positive enthalpy of reaction. Those tie together. And we have a magnitude. So the amount of energy that got absorbed here, numerically, is 182.6 kilojoules. That's the amount of heat being absorbed when 1 mole of nitrogen reacts with 1 mole of oxygen. Now notice, these are based on balanced reactions. So these delta H of reaction is based on the balanced reaction as given. So that means I have to have 1 mole of nitrogen reacting with 1 mole of oxygen, so on and so forth. If I change that number of moles, I change the enthalpy of reaction. I increase or decrease that kilojoule value. So that leads to stoichiometry again, which is what this chapter is all about. How do we use that stoichiometry? We can apply that to heat of reaction as well. The amount of heat being emitted or absorbed by that chemical reaction depends on the amounts of reactants that you actually have, not just the balanced equation, but the real situation. Okay, so actually reacting. Now we usually specify the change in enthalpy of a reaction in combination with balanced chemical equation. You usually get both pieces of information. If you're given one, you'll need the other, or it may give you enough information to balance an equation, but you'll need both. The magnitude for the heat of reaction is for the stoichiometric amounts, as we said, as written in the balanced equation. Okay, so that only applies to the equation they give you. Now, there may be situations where they give you a heat of enthalpy and they've gone ahead and multiplied up the number of moles that are in the reaction. So you don't want to divide those out without changing the enthalpy as well. Let's look at an example of this. Let's take the combustion of propane, which is in LP gas. Okay, so C3H8, and for this one, we need 5 moles of oxygen for every 1 mole of propane. We produce 3 moles of carbon dioxide and 4 moles of water. Okay, so take a minute, check and make sure that you have a balanced equation. So carbon balances on both sides. We've got 8 hydrogens on the left, and 4 times 2 is 8 on the right. 5 times 2, we've got 10 oxygen on the left. 3 times 2, we've got 6, plus 4, 10 on the right. Doesn't hurt to make sure you've got a balanced equation before you start. Okay, so that's good. And then the other thing they've given us is the enthalpy of the reaction. And we can see that it is negative, which is what we expect for combustion. We expect it to give off heat. Negative 2,044 kilojoules when I react 1 mole of propane with 5 moles of oxygen. Okay, these two are tied together. I can't separate those. All right, so stating in words what we just said, what we just looked at. 1 mole of propane reacts with 5 moles of oxygen, forms 3 moles of carbon dioxide and 4 moles of water. 244 kilojoules of heat are emitted. Okay, that's what the negative is telling us. They're being given off. Now, since I have a balanced equation, I can use my stoichiometry. I can use the ratios to construct conversion factors between amounts of reactants or products and now that quantity of heat. I can relate those number of moles to that enthalpy value. So for example, if I want to find out how much heat I can get from the combustion of a mass of propane in grams, what I want to do is start with grams of propane, and I want to end up with kilojoules of energy. Again, I can't go directly from grams to kilojoules. Moles, that's my universal translator. Notice in every reaction we've done here, it's mole in the middle, okay? Keep that in mind. It's mole in the... Oh, goodness, you silly thing. There we go. My apologies, my touch screen is a little bit too touchy. Okay, so mole in the middle, remember that. You got to go through moles to get to anything. So the first thing I'm going to do is convert from grams to moles using the molar mass of propane. So when I look up 3 carbons plus 8 hydrogens, I find that it's 44.1 grams in 1 mole. Okay, once I have moles of propane, then I can convert to kilojoules using the coefficients in the balanced equation and the enthalpy. Okay, so that can be used, that enthalpy can now be used just like a coefficient. There are negative 2,044 kilojoules for every 1 mole of propane, as shown in the balanced equation. Now, if I were basing this off the amount of oxygen that I have, I would have to say 5 moles of oxygen. If for some reason I was using the carbon dioxide, I would have to use 3. If I was using the water, I would have to use 4. I have to relate it back to the amounts. So be careful on this one. Okay, that is from the balanced equation. That is not just 1 mole like you see with grams per mole. Little bit different there. This one is always 1. Okay, this one, when you're relating energy to moles, not always 1. All right, so let's put an actual value on that. Let's get some grams of propane in there. So we've got our home barbecue, one of the gas tanks of propane like you buy to run your home grill, and it has 11.8 times 10 to the third grams of propane in it. So 11.8 kilograms. I want to know how many kilojoules of heat I can get out of that tank of propane. So I go back to the information I'm given. C3H8 plus 5O2 yields 3 CO2 plus 4 H2O. And I've got my enthalpy of reaction, negative 2,044 kilojoules. So now I'm going to write it out here, but in the next couple of slides it walks through a little bit cleaner. You'll be able to read it a little bit easier, but I want you to see it kind of written out. So 11.8 times 10 to the third grams of the propane. Now, in order to relate it to the number of joules, I need, or kilojoules in this case, I need to know moles. I cannot go directly to the kilojoules from the grams. I have nothing to relate it to. I can only relate kilojoules to the coefficients in the balanced equation, which is number of moles. So remember we said that we have 44.11 grams of C3H8 for every 1 mole of C3H8. So grams have canceled out. Now I know how many moles of propane I have in the tank. Okay. And now if I look at propane, it's an understood 1, so I have 1 mole of propane in my balanced equation, and I have a negative 2,044 kilojoules for that. So very simple, very easy way to lay that out. I get a negative 5.47 times 10 to the 5th kilojoules. Okay. So if you want to write that out, okay, 547,000 kilojoules of energy from that tank. Now, you may not be as familiar with kilojoules. You could do a conversion to change it to BTUs or whatever energy unit you're comfortable with to see how much energy you're going to get out of that. But we're going to leave it in kilojoules. The negative value is just telling us that that's the amount of heat given off by the reaction as that propane burns. All right, so here's the cleaner version. Solution map from grams to moles to kilojoules we already looked at. And here are the relationships that we used. Okay, so from the balanced equation, we have the 1 mole of propane to the negative 2,044 kilojoules of energy, and the molar mass of propane that's calculated from the periodic table. Okay, again, can't emphasize it enough. Make sure you're taking the values of the energy to number of moles from the balanced equation. Number of moles, not always 1 in that case. And then setting it up to work it out, there you see the final value that we got, the negative 5.47 times 10 to the 5th. Now, often in the homework, you will see that they ask for just the absolute value of Q. They just want to know what is the quantity for the heat, either being emitted or absorbed. And then they ask for words to convey the sign. So instead of saying positive or negative, they're going to ask you to say that 5.47 times 10 to the 5th kilojoules of energy were emitted. Okay, so in this case, you wouldn't put the negative, you would say emitted. And the reason for that is to be sure you are truly grasping the concept of what the positive and negative mean, that energy is absorbed or emitted, that it's giving off heat or it's absorbing heat. Is it going to feel hot or cold? So that's enthalpy in a nutshell. But one more thing that they're going to tie it to, you have in your book the everyday chemistry boxes that you come across. And this is the one on page 265. And it talks about Bunsen burners. Now, we've not used a Bunsen burner yet in the lab. A lot of times we have kind of moved away from having open flames in the lab when it's a multiple use lab, just because there tend to be a lot of flammables involved. You'll see a lot more hot plates. But Bunsen burners are still a very valuable tool to have in the lab. Now, when you light a Bunsen burner, there is a valve system, a mechanism that allows you to adjust the amount of air and oxygen in the air that gets mixed with your fuel. So it's going back to that stoichiometry. Okay, so it's mole to mole of fuel to oxygen. Now, if you light a burner with the air completely closed off, which is usually how you start, you want to be burning pure methane with just the oxygen in the air around it. You're not giving it extra air. When you light the burner with the air completely closed off, what you're going to get is a yellow, smoky flame, and it's actually not very hot. And this is something I do as kind of a demonstration. You can quickly, you wouldn't want to hold your hand over it, but you can run your hand quickly through the flame, and you're not going to notice it. It's a little bit warm, but it won't burn you because it's really not very hot. So what you do at that point is you start increasing the amount of air going into the burner by opening that valve. And as you do, as you open the valve and it allows that system to draw more air and more oxygen in, you'll see that the flame goes from this smoky yellow color to a bluer color. It's less smoky and it starts getting hotter. You wouldn't want to put your hand in it. What you're looking for is the optimum adjustment at which point the flame has a sharp inner blue triangle, and there's an outer cone that, unless you're in a darkened room, you almost can't see it. It's very difficult to see under regular light conditions. It's giving off no smoke, and it gets hot enough to easily melt glass, which if you look up the melting point of glass, it's pretty impressive. I would encourage you to do that. It really kind of makes an impression how hot these things can get. And that's what you usually want to do to maximize the efficiency of your burner. You want a hot flame so you can heat things more effectively. Now, there actually is a point at which you can add too much air. If you continue to add air beyond that point, more isn't always better. You can actually cool the flame off to the point where you actually extinguish it. You give it too much oxygen and it can't continue burning. It actually swamps the reaction. And here's just a visual of what you see. So this is in A, what you see when you start with the valve closed. There's no air coming into it. There's a little bit of blue at the bottom, but you mostly get this smoky orange flame, very tall flame as well. As you start to add air, you'll see that it gets bluer, you'll see that you're starting to get a little bit of an inner cone, but you still have this kind of yellow at the top. All right, here's what you're shooting for right here. You've got this inner cone. That is hot, and the tip of that inner cone is actually the hottest part of the flame. And then there's the outer one. They've got it in a dark room so you can see it, but in a regular light situation, you probably wouldn't even see the outer cone. But usually, this is your heating point right here. You're going to put whatever you want to heat down in just to the tip of that inner cone. That is the hottest part. That's where you're going to melt glass. And then as you continue going, if you add too much air, you'll see that the flame begins to get a little bit orange again. It starts to lose that inner cone. And you'll notice right here at the source, even though it's burning around the outside, it's actually extinguished itself right over the top of the burner. There is no flame there. It is just gas and air blowing out. It can't combust because there's too much oxygen. Now, let me go back to that one. So what they're challenging you to do with that little notice about the everyday chemistry is to use the concepts that you learned in this chapter about stoichiometry and about enthalpy to explain the changes that you see in the Bunsen burner in each of these steps. How can the stoichiometry help to explain what's going on in each of these? So I would challenge you to do that. See if you can think about enthalpy. Think about the reaction that's going on here. If we are burning, again, natural gas, if we're burning, you can use any of them, but just, oops, not CH3, CH4. If you look at the combustion of CH4 with O2, and I'm not going to balance it for you. You've had that done, so you can go back and balance that. But if this were the reaction you were looking at, and it's not methane we're burning, it's something else, but look at it and see, can you use stoichiometry to explain, and enthalpy to explain what's going on in each of these? Okay. So see if you can explain that. We'll look at that more on Friday. This wraps up Chapter 8. Next, Chapter 9, we will start looking at the makeup and build of atoms in the periodic table. We're going to start looking at their very inner structure and how that affects bonding.